Classifying sets and subsets of rational numbers. Natural numbers are the set of counting numbers. You learned how to count this way when you were little. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the natural numbers. Whole numbers are the set of natural numbers and 0. Most little kids don't start counting 0, 1, 2, 3, 4, 5. But when we add the 0, we're talking about the whole numbers. Let me highlight that 0. Here's our natural numbers. So you can see the whole numbers have 0 and all the natural numbers. Our integers have our natural numbers, and they have 0, and they have the opposites of the natural numbers. So that is the set of whole numbers, their opposites and zeros. And 0. Rational numbers, that's just any number that can be written as a ratio of two integers. So -9/4, that could be a ratio of -9 and 4. It could also be a ratio of 9 and -4. That would be equivalent, right? So -9/4 could be either of those. What about -2? You might be saying, well, that's not a ratio. It could be, though. It could be a -2/1. 1.3, that could be a 13/-10. So any number that is a rational number can be written as a ratio of two integers. All of the integers are rational, all of the whole numbers are rational, and all of the natural numbers are rational. So you can see that numbers can belong to more than one set. Let's talk about how these sets are related. So we're going to use this diagram, and right now I just want you to add some words here. Let's add some labels. We're going to have the natural numbers, the whole numbers, the integers, and then the rational numbers. And we'll talk about why they are in the order that they are in just a moment. For now, I want to talk about a real-world analogy that can help you understand this diagram. What I want to talk about is America and Texas and Garland. This is the United States. And this little area is supposed to be Texas. And then inside Texas, this is the city of Garland. I do actually love art, I promise, but bear with me here because these regions were a little bit challenging for me to draw. All right, so right now you are probably sitting in a school in Garland ISD, which means you are in Garland. Garland is in Texas, so you're in Texas, and you're also in the United States of America right now. And I realize I left out Alaska, Hawaii, Puerto Rico. This isn't the complete version of the United States. It's just a region representing it that was as close in shape as I could make it. All right, so if I was going to draw a diagram similar to the one over here, but representing locations, I might start with Garland. There it is. And then draw Texas around it because Garland is inside Texas, and then draw the United States around that because Texas is inside the United States. Wherever you go in Texas, you are inside the United States, right? So let's think about where we could place some locations within this diagram. First, I want to do the Garland Square. So the square in the middle of downtown Garland, you know, it has that cute little playground, lots of nice restaurants, a big green space. That's inside Garland. I'm going to put it right there. Let me ask you a question. Could I put the square here? No, I couldn't. The square is in Texas, right? But if I put the Garland Square here, then I'm saying it's not in Garland, and it is in Garland. So so the Garland Square needs to be inside the Garland region. If I put it outside of that, I'm saying it's not located in Garland. All right, so let me erase that. Let's think about something that would be outside the Garland region, but inside the Texas region. You know what I'm thinking about is Six Flags Over Texas. I love going to Six Flags Over Texas with my family, but we have to drive a little bit. It's in Texas, but it's not in Garland. So this is where that would belong. And then let's think about something that's outside of Texas, but is inside the United States. How about the Statue of Liberty? That is outside of Texas. It's inside the United States. It's outside of Garland. Okay, so that shows how those are related, right? The Garland Square is inside Garland. It's also inside Texas, and it's inside the United States. Six Flags Over Texas is not in Garland, but it is in Texas, and it is in the United States. And the Statue of Liberty is not in Garland nor in Texas, but it's in the United States. If you can understand how this diagram works, you can classify numbers as well. You just need to know the definitions that we've already established. All right, I have a strategy that I like to use when classifying numbers. I like to organize them using a table. And here's how I do it. I write down the sets that I'm being asked to compare. So in this case, rational, integer, whole, and natural. And then I write down my numbers across the top of my table like this: negative 4.5, 710, negative 12, 7/8, and 0. Now, I always want you to consider, do you think that these numbers are simplified? Like, for example, if I had a number like 4/2, I would rewrite that as 2. I would simplify it. I don't think we have anything like that here. I think we have values that are already simplified, so we're good to go. Let me draw some columns to make this easier to read. There we go. All right, so negative 4.5. Let's think about this. Is this a rational number? Could I write it as a ratio of two integers? Well, I could, right? Because negative 4.5, that could be negative 9/2. It could be 9/2. Negative 9 and 2 are both integers. 9 and negative 2 are both integers, so this is rational. It is not an integer. Remember, our integers are our natural numbers, their opposites, and 0. So it's not an integer. It is not a whole number, and it is not a natural number. 710 is rational. You could write it as 710/1, right? It's an integer, it's a whole number, and it's a natural number. When you were little, you probably didn't count all the way to 710, but if you counted 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, and you kept going, you would eventually get to 710, right? Negative 12 is rational. We could write it as the ratio of negative 12/1. It is an integer. It's the opposite of 12. It is not a whole number. There are no negative whole numbers. And it's not a natural number. All right, so rational numbers, 7/8. Yes, because 7/8 is the ratio of 7 to 8. That's a ratio of two integers, but it is not an integer. It's not a whole number, and it's not a natural number. 0 is rational. 0 is an integer. 0 is a whole number, but 0 is not natural. All right, so now we know which sets each of these numbers belong to, and a lot of them belong to more than one set, right? That's okay. Even though they have more than one set they belong to, they're only going to have one location where they can be placed on our diagram. That's important to remember. All right, so let's start placing these. I want to start with my natural numbers. Let's see, 710 is the only number that is a natural number. So let's put it down here. There we go. It is also a whole number, an integer, and a rational number, right? And so you can see 710 is inside the natural number region, it's inside the whole number region, the integer region, and the rational number region. Let me ask you a question. Since 710 is a whole number, could I put it here? No, I couldn't put it there. This would be wrong because if I place it there, I'm saying it's a whole number but not a natural number. So 710, even though it's a whole number, it can't go here. It needs to go inside the natural number region. All right, let's look at our next set of numbers. That's going to be our whole numbers. We said 710 is whole. It still is. And then 0 is also a whole number. So 0 is whole, but it's not a natural number. So it's going to go right there. All right, let's work our way down to our integers. 710, whoops, need a different color. 710, we were saying, is an integer. And it's a whole number and a natural number. We already did 710. Negative 12 is an integer and 0 is an integer. All right, we don't need to write 0 because we already have it in the right place. And we already have 710 in the right place. So we're going to put negative 12 right here, and it's the only one that's going to go in that area. 0 is an integer, but it's already inside the integer circle, and it's also inside the whole number circle where it's supposed to be. All right, let me do my little yellow circle there. And then next up, we're going to do our rational numbers. And look at this. They are all rational. 710, negative 12, and 0 are all rational, but we've already done those. So we're just going to focus on the ones we haven't done yet. That would be negative 4.5, negative 4.5. And then negative, I'm sorry, not negative. 7/8. There we go. So negative 4.5 and 7/8 are rational, but they're not integers, whole numbers, or natural numbers. So they belong in this red region right there, the one with the red circle. All right, so this is one way that we can represent the classification of these numbers. And I really do think it helps to draw a table. This diagram is really similar to the one that we just looked at, except for it is a Venn diagram. It shows all of the ways in which these values in which these sets of numbers relate. So let's look at how to make a table for these numbers. Let's start with a table. In your table, I want you to include rational numbers, integers, and whole numbers. All of these numbers appear to be simplified, so let's think about where they belong. So 3/4 is rational because it's the ratio of 3 to 4. It's not an integer though. Negative 92 is rational and it is an integer, but it's not a whole number. 5.2 is rational, but it's not an integer or a whole number. Negative 1/2 is rational, but it's not an integer or a whole number. And 19 is rational, an integer, and a whole number. Great, so now they're classified. I'm going to kind of color code a little bit here. I'm going to make my integer region red and my whole number region blue and my rational number region green. There we go. That looks pretty good. All right. So first I want to start by, I think I'm going to just work from whole numbers up. Let's see. What did we say was a whole number? Just 19, right? Just this one right here. 19 is a whole number. So where can I place it? Let's see. It's a whole number, and it's also an integer, and it's also a rational number. So it's going to go in the area that has all three of those. It belongs to all three sets. That means it has to go there. And it's the only number that's going to go there because it's the only number that belongs to the set of rational numbers, the set of integers, and the set of whole numbers. It needs to be in all three of those regions. All right, next I'm going to look at my integer row, and I see that on that one I have, let's see, negative 92. Okay, so negative 92 is an integer, and negative 92 is also rational. So it needs to go in my red and green regions. So negative, whoops, let me change the color of my pen. Negative 92 is going to go there because it's both integer and rational. Now my remaining three are only rational. There they are. So they're only going to go in the region that shows rational numbers. So 3/4 and 5.2 and negative 1/2 are going to go out there. Now, we have them classified. Our table matches our diagram. This looks good. But one thing I want to point out is that we have a lot of empty regions. I want to kind of explore why that would be the case. So this region right here doesn't have any values in it. And that's because there's no such thing as an integer that's not rational. All integers are also rational numbers, so there's never going to be a value there. And then this region here is also empty. And that's because you can't have whole numbers that also aren't integers, and you can't have whole numbers that aren't rational. So this area is always going to be empty. This doesn't seem to be a very efficient diagram. It has a lot of empty space. If we wanted to represent these relationships more efficiently, we could do it like this. It's going to show the exact same information, but using an Euler diagram that's not a Venn diagram. Venn diagrams have to show all the overlapping regions. But we're going to just show the ones that we need right now. So in our whole number section, we're going to have 19. 19 is a whole number, an integer, and a rational number. In our integer section, we're going to have negative 92. Negative 92 is an integer and a rational number. And then in our rational number section, we're going to have 3/4, 5.2, and negative 1/2. And those are rational, but they are not integers or whole numbers. It could be helpful here to have my circles. So I have my whole number circle. Only 19 is in the blue because only 19 is whole, right? But 19 is also inside the red because 19 is also an integer. And negative 92 is also in the red circle because it's also an integer. And then my rational numbers, I'm going to have my green circle here. So negative 92 and 19 are inside the green circle. And then 3/4, 5.2, and negative 1/2 are also in that circle. Although those last three numbers are only in that circle because they're not integers or whole numbers. So these two diagrams show the same thing. They're just two different ways of representing it. Sometimes an Euler diagram is a little bit more efficient. All right, so this diagram is only comparing integers and whole numbers. Go ahead and make your table. All right, so 24 is an integer and a whole number. Negative 2 is an integer but not a whole number. 5 is an integer and a whole number. Negative 8 is an integer and not a whole number. And negative 11 is an integer and not a whole number. Great. So now we know which sets these are going to go to. 24 and 5 are both whole numbers and integers, so they go in here. And negative 2, negative 8, and negative 11 are integers, but they're not whole numbers. So they're going to go in this area out here. Beautiful. Could we show that same information using a Venn diagram? We sure could. So here we would have integers, and here we would have whole numbers. And then 24 and 5 would be in the overlap because they're both integers and whole numbers. But negative 2, negative 8, and negative 11 would be in the integers only section because they are integers and they are not whole numbers. Now let's try it with integers and rational numbers. Let's start with negative 25 hundredths. It is rational, but it's not an integer. Negative 9/10 is rational, but it's not an integer. Negative 4 is rational and it's an integer. 124 is rational and it's an integer. And 19 is rational and it is an integer. Beautiful. All right, now I do want to point out that that positive 124 and 19 are also natural numbers and they're also whole numbers. So the most specific classification is actually not something that we're talking about here. We're not talking about how to classify them in their most specific classification here. We're just asking, are they integers and are they rational numbers? So we're looking at those two sets specifically here, but we do know they could be classified more specifically than that. It's just not what this problem is asking us to do. And that's okay. We don't always have to consider every single set that a number belongs to. All right, so we know where these belong in this diagram. We know that negative 25 hundredths is going to be only rational. And negative 9/10 is going to be only rational. They won't also go in the integer area. Negative 4 is belonging to both. 124 belongs to both, and 19 belongs to both. So why is this region over here empty? Why is there nothing in this section? That's because it's not possible for something to be an integer but not be rational, right? There's no such thing as an irrational integer. So that space is always going to be empty. In fact, we might say that it would be more efficient to represent this relationship with an Euler diagram that's not a Venn diagram. In this case, we'd have negative 4, 124, and 19 here. They're integers. And out here, we'd have negative 25 hundredths and negative 9/10. And really, this is showing the same thing, right? It just doesn't show the empty region where we couldn't possibly have any values.